We are in the thermochemistry lesson and we have discussed some basics and we entered into the heat of reactions for and also heat of the process if it is a physical process. And in the process, in the learning process, we have also defined something called enthalpy of formation, and also we wrote a formula for enthalpy of reaction as enthalpy of products minus enthalpy of reactants, and absolute value of entropy is not possible to determine. Therefore, we have arbitrarily assigned a standard state indicating at the standard conditions the enthalpy of elements is arbitrarily assigned to zero values, and for other compounds the enthalpy values can be determined using several thermochemical equations. And enthalpy conditions other than standard conditions will be the heat changes involving when the substance at standard state is brought into the a state where we are interested. So, and also when we are talking about enthalpy of formation, I gave this equation and I gave this uh, enthalpy values. Actually this enthalpy value is value of other equation, that is actually H2 plus I2. So what I do here, I make slight changes. This one is I2 for combustion. This is H2 plus O2 is combustion, which is exothermic reactions. It's very wrong way of writing the data. So therefore this is HI. And actually here we are getting a 2 moles of the substance. Therefore it is not called as a formation reaction. In the formation reaction we must always have 1 mole of the product. Therefore, so to have 1 mole of product we must use half mole of H2 and half mole of iodine. Now this is the formation uh, enthalpy or enthalpy of formation of hydrogen iodide at the standard states. So what is enthalpy of formation? Enthalpy change associated with the formation of 1 mole of compound from its constituent element. If that change at the standard conditions is known as a standard enthalpy of formation. Okay, now let's take one more example here and let's try to define what is enthalpy of a compound and what is enthalpy of formation. So let me take the example of carbon. So let's take carbon at the standard condition exists as graphite and oxygen is O2, which is gas, and giving us carbon dioxide gas. Okay, and if we apply the enthalpy of a reaction formula, that is delta H, let's say we are in standard condition. So delta H naught reaction is equal to summation of enthalpy, standard enthalpy of products, that is carbon dioxide. So let's take the formula first, then we go for applying this formula to the above equation, that is summation of enthalpy of products minus summation of enthalpy of reactants. Okay, product is a compound here, therefore I can write here this is H naught of carbon dioxide minus, there are 2, therefore I must use the addition. So that is enthalpy of carbon graphite, therefore I write graphite here, plus H naught O2 gas. Okay, and delta H naught reaction, that's going to be a formation of carbon dioxide, and the heat associated here is therefore I can say this is delta HF naught of carbon dioxide. That's going to be simply, there is only one carbon dioxide and there will be no summation here because as we have only one reactant, that's going to be enthalpy of carbon dioxide. What does it mean? It means enthalpy of a compound is simply enthalpy of formation of the compound. Therefore, we have a formula. What is that one? Delta H naught reaction or delta H reaction simply is equal to summation here the H naught products, that means that is delta HF formation of products minus summation of delta HF formation of reactants. So why are we using the summation here? In many reactions, we have more than one products and we have more than one reactants. And one more thing here, we must consider the summation involves every product and every reactant, including their entire moles. So therefore, the formation is actually defined for 1 mole of the substance. If you clearly have a look on the definition, it is associated with the 1 mole of formation. So in the reaction enthalpy, so when we write the enthalpy of products, if there are, let's say, 2 moles of a particular substance formed, and we must multiply that 2 with the enthalpy of formation of product if it is a product, and if it is a reactant we must place here. So therefore, to simplify and to have a great clarity, so we try to have coefficients of the reactants associated with the enthalpy of formation. Therefore, we slightly tweak this formula so that it will serve our purpose. So that is delta H naught reaction, that's going to be summation, and I write NP, so where NP is number of moles of products, and HF naught of products. So products minus summation NR delta HF formation of reactants. This is formula for enthalpy of a reaction. If it is a standard enthalpy of a reaction, we must use standard conditions. If it is other than standard conditions, the only difference is there will be no standard condition denotation description. That is simply delta H reaction is equal to summation NP delta HF of products minus summation NR delta HF reactants. So this is the formula for enthalpy of a reaction. So we must know each and every substance involving in the reaction enthalpy of formation values and the stoichiometric coefficients involving in the reaction. So then we will be able to find out delta H reaction for that balanced reaction. Now let's go to the next one. How this delta H reaction can be applied for some problems where delta H reaction can be find out using the HF values, that is formation values. So that we will do now. So okay, now the problem is, okay, give me 1 second, I want to pick the problem from the textbook because these problems are difficult to memorize. Okay, very famous reaction which is Thermite reaction. So now the problem is on Thermite reaction. The problem is this one. Using enthalpies of formation, so calculate the standard change in enthalpy, standard change in enthalpy for the Thermite reaction. And what is a Thermite reaction? Thermite reaction is producing the iron from the iron oxide using aluminium, which is used in connecting the broken rail tracks. So one of the famous application of chemistry. Actually, the heat evolved is so high that iron comes in the form of liquid, but for the sake of the problem, let's use the iron as a solid here. So now what we require, and to find out enthalpy change for this reaction, we must know enthalpy of formation of every substance involving in this reaction. So, and which enthalpy change here? That is standard enthalpy change. Therefore, standard enthalpy of formation value for elements at the standard state is simply 0. This is pure aluminum, this is pure iron. Therefore, delta HF formation of aluminum solid is 0, and delta HF formation of uh, iron solid is 0. And there are other ones, that is delta HF formation for Fe2O3 solid, that's going to be negative 826 kilojoules per mole. And what is the other substance we have? Delta HF formation of Al2O3 solid, that value is negative 1676 kilojoules per mole. Okay, now having the data in our hand, now we are going to find out the enthalpy change of the reaction at the standard states. Therefore, that is known as standard change in enthalpy. So what is the formula? We know the formula. Delta H naught reaction is equal to summation NP delta HF naught products minus summation NR delta HF formation of reactants. So here we have the two products and two reactants. So Al2O3 is 1 mole, therefore Al2O3 eta formation must be multiplied with coefficient 1. So the data given here is per mole, and we should be careful with the moles of the each substance in the reaction. So for aluminum, for iron, its eta formation must be multiplied with 2, and fortunately here its value is 0. 2 times 0 is going to be 0, and same is the story with the aluminum. Now if we apply the if we substitute the values, so therefore what are the products here? The products here is Al2O3, and what is the Al2O3 eta formation? That is negative 1676 negative, and there is a 1 mole, so we must write 1 mole times negative 1676 kilojoules per mole plus 2 mole iron, and its enthalpy of formation value is simply 0, minus, so 1 mole of Fe2O3 is there, and its enthalpy of formation value is negative 826 kilojoules per mole plus 2 mole times, and what is the enthalpy of formation of aluminum solid? That is 0, standard state, as we are calculating the standard enthalpy change. Okay, for the same aluminum and iron, if they are not in the standard state, they do possess the enthalpy formation values. So if we do this here, so mole and mole cancel out. Now we get negative 1676 kilojoules. This is 0, minus, and mole and mole cancel out. We get negative 826 kilojoules. So delta H naught reaction. So delta H naught reaction is equal to negative 1676 kilojoules, negative times negative positive 826 kilojoules. So that will give us, if we do the mathematics, what we get? 0, 5, okay, negative 850 kilojoules of heat. That is negative. So what does it mean? In this reaction, 850 kilojoules of heat will be released with the formation of 1 mole of iron. So if we look at the balanced equation, what it clearly tells us, 2 moles of iron, sorry, here it is 2 moles of iron. So each for every 2 moles of iron production, there will be a release of 850 kilojoules of energy. And it is such a high energy that uh, that makes the iron into liquid form, which is for metals we call it as a molten. So now the iron solid, which is coming out of this reaction along with the heat, becomes molten liquid, molten iron. And that molten iron, you can place it on a broken railway track, and you can make it to fall on that broken area, and after some times it solidifies and clearly gives a correct connection between the broken rails. So that's how we will we the broken rails were repaired in the earlier times. So this is about the heat of reactions, and there are many problems. We shall have a separate session on the problems. Now we shall continue with the so enthalpies of several kinds of reactions. And now we are dealing standard conditions, therefore we stick to our discussion to standard enthalpies. That's now we are dealing standard enthalpy of combustion. So therefore this is enthalpy associated with the combustion reactions at standard states. So how it is defined? This is enthalpy change associated to combustion reactions. Combustion reactions. As it is a standard state, that means at 298 Kelvin and 1 atmospheres. So combustion reactions enthalpy change at 298 Kelvin and 1 atmospheres, and enthalpy changes, and we must use one condition here. What is that? In the combustion reactions, in some kind of reaction there will be formation of 1 mole of substance, or you can say 1 mole of substance can be combust in a balanced reaction. In some reactions several moles of the substance is combust. Therefore what happens? So there will be some kind of discrepancy. Therefore to avoid that discrepancy we must have a clear definition. So what is the heat of combustion now? Standard enthalpy of combustion, that is standard enthalpy of combustion, as it is a combustion reaction I am writing as combustion, is defined as enthalpy change. Generally in the combustion reactions heat will be released. Heat released when 1 mole of a substance undergoes combustion. So that heat is known as a heat of combustion. So what are the examples? Let's say methane combustion, that is we must take 1 mole to O2 gas will give us CO2 gas plus 2H2O gas, 2H2O liquid, and delta H naught combustion for this reaction is negative 890.3 kilojoules per mole. So this is with respect to the methane. So what is the combustion of hydrogen? So as we are doing the combustion of hydrogen, hydrogen must be 1 mole. So in the thermochemical equation, therefore that is H2 gas. To do the combustion of 1 mole of hydrogen, we must use half mole of oxygen gas, and we will end up with H2O liquid 1 mole. And what is the combustion or heat of combustion or energy released here in the combustion of 1 mole hydrogen is negative 285.29 kilojoules per mole, which in other terms basically it is a delta H naught formation of H2O liquid. Okay, this is about the combustion formation, combustion enthalpies. Now let's go to the acids and bases. When the acids and base react, energy will be released. and that process is known as a neutralization. Therefore, that is known as a heat of neutralization. In clear words, we can say enthalpy of neutralization. So at standard conditions, so we try to find what is the enthalpy of neutralization at standard condition. That is standard enthalpy of neutralization. So what is this? This is the enthalpy change associated. We can say this with respect to base and with respect to acid. Therefore, enthalpy change associated with the neutralization of a base against acids. And this is known as a delta H naught neutralization of a base. Neutralization of a base. And same thing if we say with respect to the acid, and we call it as delta H naught, standard enthalpy of neutralization of an acid. So generally, if you take the strong acid and strong base like NaOH, we can express that with respect to NaOH and the acid HCl. So both are strong acids, NaOH aqueous, HCl aqueous in a dilute conditions. So in the definition we must use the word dilute conditions, and we get NaCl, that is in the aqueous conditions, plus H2O liquid. And for the 1 mole neutralization of NaOH or 1 mole neutralization of HCl, the enthalpy or heat released is 57.32 kilojoules. I said heat released, but when we write the thermochemical equation, we must use the negative sign for the release of heat. So we must be very careful. That's a mistake I committed in the last class, where I used data of the heat data of one reaction with the other reaction. So that's a very bad mistake. Now I want to be very clear here. So here in this process, the enthalpy change is negative 57.32 kilojoules. Now let's try to simplify this little more. So this is the overall molecular equations. Let's try to have a complete ionic equations. Why? Because these are compounds, when as they are strong electrolytes, they dissociate into ions in the water completely. So therefore NaOH basically present as Na plus aqueous and OH minus aqueous, and HCl is also a strong acid, therefore it exists as H plus and Cl minus ions in the water. So these, after combining, after the reaction, we have Na plus ions and Cl minus ions, and H plus ions and OH minus ions combine, and that will give us H2O liquid. This is total ionic equation. So in the process, if we carefully consider, before the reaction we have a sodium ion and chloride ion. After the reaction also sodium ion and chloride ion. So with respect to sodium and chloride ions, in the reaction there is no change. The change basically happened with these two species, OH minus combining with H plus to produce H2O liquid. So therefore, what is neutralization? Neutralization is essentially process of formation of 1 mole of water. So in the process, the heat released is actually, the neutralization is known as, for the complete neutralization of 1 mole of H plus ions with the OH minus, energy released is known as enthalpy of neutralization. So here it is delta H naught neutralization is negative 57.32 kilojoules per mole. Both are strong acid, and this is the general thing for strong acid versus strong base we can use in the place of HCl, we can use HNO3. In the place of NaOH, we can use KOH, etc., etc. And what is the case when we have a weak acid versus strong base? Do we get the same amount of heat? Let's see. This is actually I am saying from uh, observed values. Okay, so let's take a weak acid, that is CH3COOH aqueous, and weak acids do not dissociate completely into ions. They mainly exist as a molecular species. They don't exist as ions in a predominant form. So the predominant form is acetic acid alone, and base, let's say NaOH. This is the molecular equation I am writing. Later I write the complete ionic equation and net ionic equation. This is going to be CH3COO Na aqueous plus H2O liquid. And what is the recorded value of neutralization for this weak acid versus strong base? That is negative 55.23 kilojoules. So that means the heat of neutralization, that is heat released in the weak acid versus strong base neutralization, is smaller than the heat released in the neutralization of strong acid versus strong base. Why it is so? Let's see. In the strong acid versus strong base, we clearly have H plus ions and OH minus ions, and they are combining and producing the heat. So in the case of weak acids, we do not have H plus ions readily. OH minus ion every time should go to the molecular species and should pick the hydrogen ion from there. So in other words, basically we have a weak acid equilibrium, existing molecules in a predominant number, and H plus ions are existing in a very little amount. OH minus ions in the medium go and pick the hydrogen ions and they become water. Now with the loss of H plus ions, which are products in the equilibrium is disturbed, and as per Le Chatelier principle, the remaining molecules of acid will dissociate into ions, and for that process it needs some energy. Therefore here, so bit of energy when compared to the strong acid versus strong base is going into the dissociation of the weak acids. So that we can clearly understand from total ionic equation and net ionic equation. So what is that? So if I write that total ionic equation, this is a predominant species, that, and what are the species? NaOH is not predominant, it completely dissociates into ions. So and we get CH3CO minus, which is a salt, completely dissociates into ions. H2O liquid. So let's see, before the reaction we have Na plus, after the reaction we have Na plus. So there is no involvement of Na plus ions literally in the reaction. So what are the species involving in the reactions? So these two on the reactant side, and product side these two. Therefore CH3COOH aqueous, this is a net ionic equation, plus OH minus aqueous, giving us CH3COO minus aqueous plus H2O liquid. So OH minus ion basically reacting with H plus ions coming from the COH. So if the the CH3COH completely dissociates into H plus ions and acetates, the heat released will be same as the NaOH and HCl. Here, as this is a weak acid, very few H plus ions are there. Therefore, the OH minus ions combine with those few H plus ions and they become water. Heat will be released. Now, the remaining acid must split into ions. So, for that process, as it is a decomposition, it requires some amount of energy. Therefore, so what is the difference? The difference is negative 57.32 kilojoules for a free hydrogen ion and free OH minus ions. When hydrogen ion is not free, so that energy is negative 55.23 kilojoules. So what is the gap here? The gap is essentially some 2 point something, that is 2 point kilojoules heat is actually going into dissociation of acetic acid. Therefore, this one we can say 2.09 kilojoules per mole uh, heat, we can call it as dissociation energy of acetic acid. Yeah, so 2.09 kilojoules per mole energy goes into dissociation of acetic acid to form acetate ion and H plus ions, and those H plus ions then combine with OH minus ions to form the H2O liquid. So this is known as heat of neutralization. Heat of neutralization for strong acids versus strong bases are higher than the acids and bases that involve weaker species. And another heat of enthalpy change is we are going to discuss is enthalpy of dissolution, which is a physical process. And what is that? When one mole of a substance is dissolved in a particular solvent, the enthalpy change associated in the dissolution process is known as heat of dissolution. Enthalpy standard, if it is at standard conditions, we can call it a standard enthalpy of dissolution. That is delta H naught solution or dissolution. So that is going to be enthalpy change associated at the standard conditions for the dissolution of 1 mole of solute in a adequate quantity of solvent. So that enthalpy change is known as heat of dissolution. And if the water is the solvent, and that is known as heat of hydration. That is known as heat of hydration. When the heat of dissolution is known as heat of solution, you can call it is known as heat of hydration if the solvent involved is water. And what is the standard enthalpy of solution is enthalpy change associated with 1 mole solute dissolving in the solvent. That is known as enthalpy of dissolution at standard conditions. If we are not at standard conditions, we simply call it as enthalpy of dissolution. So that's about enthalpy definitions for several processes like formation, neutralization, combustion, and for reactions also we derived a formula, and other one we have is enthalpy of dissolutions. Before we end this class, we must have some clarity over the enthalpy of reaction formula, how we arrived at that formula. So delta H naught reaction, let's fix to the standard conditions. That's going to be summation of delta HF naught formation of products minus summation of delta HF naught of reactants. Here I did not write the coefficients of reactants and products. It is obviously understood. So how we arrived at this formula? Let's have a critical look on this. So we have reactants here, and those are becoming products. Okay, let's assume a imaginary case, a reactants going to products in such a way that all the reactants will split into their constituent elements at standard conditions. Therefore, we are getting here the constituent elements. Therefore, this is actually reverse of formation. Therefore, the enthalpy change associated with this process is negative of opposite of delta H formation of reactants. Okay, now the same constituent elements will give us the products. That means here it is the formation of the products. Therefore, this is delta H formation of products. Okay, now let's add these two, because these are the two changes happened in the overall process. Therefore, the delta H naught reaction is equal to uh, the breaking of reactants to their constituent elements and its enthalpy, plus the formation of products from that constituent elements, the enthalpy involved in that process. The sum of these two processes is known as delta H naught of reaction. That is, so delta HF naught of reactants, negative because it is a reverse of formation, plus delta HF naught of products. And if we properly organize, we will end up with delta H naught reaction is delta HF naught products minus delta, okay, let's use delta HF naught reactants. So generally we have more than one reactant and more than one product, therefore we must use summation. Therefore this is going to be summation and these are summations. Therefore, so some again one more addition. So generally formation is defined for 1 mole of the substance, and if we want to write the clear formula, we can write sigma NP delta HF naught products minus sigma NR delta HF naught reactants. So this is the formula for enthalpy change for a reaction. So in the next class, what happens to the enthalpy of a reaction when the temperature changes are involving? So basically we are going to discuss in the next class dependence of enthalpy of a reaction on temperature. That is known as Kirchhoff's equation. We will cover the topic in the next class. Thank you. Thank you very much.